Good morning, everybody. Welcome back. So where are we? Well, we're actually getting near the end of the course, aren't we? So what the topic for the next few days is sort of the culmination of the course is actually talking about electromagnetic radiation. Now, I know you don't feel expert on Faraday's law because we only spent one day on it. And there's a lot more we could do with it, but we did lose a week due to bad weather here. So what we're going to do is go on and talk about electromagnetic radiation, although we would, and I should explain that the reason we're doing things like Gauss's law and Faraday's law is so that we can actually understand electromagnetic radiation in a deeper way. So our goal today is to talk about electromagnetic radiation. I'd like to start out with something we saw at the beginning of the semester, but revisit it, which is a demo of an interesting piece of equipment. And I'm going to switch cameras here so we can see it. Okay. So let's see here. So let me remind you about what we saw. We have this object here, which is basically a power supply connected to this aluminum tube. And we also have a couple of kinds of, we have light bulbs. Here's a light bulb connected just to two wires and nothing else. And we also have a somewhat easier to manipulate object, which is really the same. It just looks complicated, but what it is this is just a really lightweight aluminum tube that's connected by screws to this plastic mounting. And then the screws, so the screws are in electrical contact. They're touching the aluminum, the metal screws, and then there's you may be able to see that there are little pieces of metal sticking up here. Let's see, yeah, little pieces of metal sticking up there. They're just soldered to the screws and then soldered to a light bulb socket. So what we've got here is a light bulb and a socket. So basically we have really the same thing here. It just has this protective plastic housing, and it's a lot easier to hold and manipulate. It's really the same thing as this. It's a light bulb connected to two metal conductors and not much else, nothing else really. And of course, we know why neither of these light bulbs is lit at the moment. It's because there's nothing that's making an electric field to drive current. So that's pretty easy to understand. What happens when we connect this device here to a power supply is a little more interesting. So all that happens when I plug it in is there's a red light that goes on. I don't know how well you can see that. There's a little red light. It's not doing anything else very interesting. But now it turns out that if I just stretch out these wires and hold the light bulb, hold them near this device, the light bulb lights actually. But if I turn it vertically, the light bulb doesn't light. And you can see that from the dangling wires that it's not connected to any power supply. Now I'm going to use the other light bulb just because it's easier to handle, and it comes out a little brighter. So we can see that when I hold this near but not touching, you can see that it's not. Let me raise that a little bit. Okay, you can see that that's not touching the metal loop. the light bulb is lit. It's still lit here. If I turn it 90 degrees, it goes out. It's on here. And interestingly, if I hold it over here, where it's parallel to the wires, but parallel to this loop, but beside it, the light bulb also goes out. Whereas if it's above it or in front of it, or a little bit, well, behind it's hard, but above it or in front of it, it's lit. So 90 degrees, it's out. Over here, it's out. But here and here and here and here and here, the light bulb is lit. And there's clearly no power supply attached to this. We just have these aluminum conducting rods, hollow rods, and a light bulb in this circuit. So the goal today is to start working on understanding what's going on in this situation. So let's think about what we actually know, what we understand now that we might not have understood at the beginning of the semester so far about what has to be going on in that light bulb to make it light. So first of all, we know that there has to be there's a current in the light bulb. So why does the bulb? Well, we understand now that there has to be a current running. So there are moving charges going through the filament in the light bulb. And we know that the moving electrons collide with the atoms, the metal atoms in the atomic cores in the filament. So moving electrons collide with the atomic cores in the filament. And in the lattice, so the lattice. And the lattice gets hot, the metal gets hot. What does it mean to get hot? Well, we know from last semester that what it means to get hot is that the metal atoms bonded together by these covalent bonds are vibrating more. They're like little masses on springs. And these little oscillating atoms on springs, so atoms oscillate. And these little quantum oscillators can give off energy. So they give off energy as light, as photons. And what makes them, why do these moving electrons move? Well, we know that the average drift speed depends on the mobility and on the net electric field inside the wire, the filament. Now the question we know why the bulb is lighting, we understand why it's giving off light, we understand what it means to have a current running through it. But what we don't understand here is what the source of this electric field is. So what's the source of the electric field that's driving this current and making these electrons all move through the filament? Well, it's definitely not a battery. It's not a time-varying magnetic field like Faraday's law, because we didn't have a loop to drive to where we could get a curly electric field. So there's there's no closed loop there. So this is a new thing. And what we want to do is understand it. So today what we're going to talk about is electromagnetic radiation, which is actually fields traveling through space. So fields traveling, I guess Microsoft Word tells me there should be one L there. Or we can say, sometimes we say propagating, and we'll see why. And by the end of today, we'll see that something interesting is possible that we hadn't thought was possible before, and that's what we're going to need Faraday's law and Gauss's law and Ampere's law, and to show that this is actually a possibility. So before we can do this, we need one more piece of physics to complete our list of equations that we can use here. So we need to modify Ampere's law slightly. So we have, remember that we have this sort of table that there are fields, they affect things, and they have sources. So electric fields, we know affect charges. Sources could be other charges, or we saw that with Faraday's law that a time-varying magnetic field could also was associated with a curly-shaped electric field that could affect other charges. Now, magnetic fields, we know that they can be made by moving charges. They can affect moving charges. Sorry, they can be made by other moving charges, but we might guess that in addition, a time-varying electric field might also be associated with a magnetic field, just sort of by symmetry of the situation. And in fact, that turns out to be true. A time-varying electric field is accompanied by a magnetic field, and we can kind of make a little argument here that shows why we might need to expect this to be true. So let's imagine that we've got a long wire connected to a power supply somewhere over here. And here's a long wire with a current running through it. It's a complete circuit, except that in the middle of it here, we've got a capacitor. So let's talk about this wire let's talk about conventional current. We'll imagine moving positive charges, conventional currents going that way, and charges, of course, building up on the capacitor, right? So we're talking about this long, drawn-out transient where we're charging the capacitor. Well, we know that this current makes a magnetic field, right? So there's a magnetic field associated with the moving charges in the current. And in fact, the magnetic field is going to, let's see, if we have our DL here, and so DL across, let's say, here's our R hat. At this location, DL across R hat is out of the page, and we're talking about conventional current positive charges. So we've got a magnetic field out of the page here. Down below, if we have a different R hat, DL across R hat, that would make a magnetic field into the page. And so what we're going to get is this pattern of magnetic field that's sort of curling around the wire everywhere along the wire. And you probably, I hope, have in your head an image of what this looks like. And this is like the program you wrote in lab to model a magnetic field due to a moving charge, right? Okay. And so we want to make sure our mathematical description of this is right, and we can use Ampere's law here. So we could draw a path, a circular path around the wire. And we consider the surface inside here. And we know that the magnetic field is going to be curling around this path. And we know the current, so we can just use Ampere's law here. And so we get that the integral of B dot dl around this round trip, around this path, is equal to mu zero times the current that's inside, the current that's piercing this surface here, which is our current I. So that's fine. Well, presumably there's a magnetic field everywhere here. There's going to be a magnetic field even around this capacitor, which actually isn't a very big part of this circuit. But we actually have a problem here because there's no current in here. So if we drew an Ampere's law path here, sort of around I'm trying to draw it so it's supposed to be path perpendicular to the page here, but I'm tilting a little so you could see it. Well, there's presumably a magnetic field here because all these moving electrons in this wire certainly contribute to a magnetic field there, but we have a problem because there's actually no current here. B exists, but I doesn't exist in here. There is no current piercing it. Although if we actually just declared that our surface stretched back here, we deformed this soap bubble so it stretched back here, then there would be a current piercing it. So we have an inconsistency here, and that inconsistency is actually solved by considering the fact that what we do have in here, even in the capacitor, even though we don't have any current, what we've got is a time-varying electric field, because as charge piles up on this capacitor, we have an electric field that's getting bigger and bigger and bigger. and it's increasing with time. So apparently dE dt is just as good at making a magnetic field as a current is. And it was Maxwell, James Clerk Maxwell, who first realized this. So this is called the Ampere Maxwell Law. And it says that it just takes Ampere's law, the integral of B dot dl around a closed, a round trip here. Is equal to mu 0 times the current inside plus a proportionality constant times our old friend, the electric flux. And the proportionality constant is mu 0 epsilon 0. So we can rewrite this with its full mathematical loveliness as mu 0 I inside plus mu 0 epsilon 0, the time rate of change of the electric flux, which is the integral or the sum of E dot n hat dA over this bounded surface. So now what we've come up with here is a set of equations that are called Maxwell's equations. Because Maxwell was the first person to write them down. They looked a little different when he wrote them because he didn't have the vector formalism, so he had lots of equations, one for every component of everything. And Maxwell's equations are powerful because they describe every possible configuration of electric and magnetic field. So you're very familiar with Gauss's law. So here's Gauss, which says that E dot n hat dA, the electric flux on a closed surface, is equal to the charge inside over epsilon 0. And Gauss's law for magnetism, which says that the integral of the magnetic flux over a closed surface is 0 because there aren't any magnetic monopoles. And we have Faraday's law, which says that the integral of E dot dl, so around a round trip path, is 0 due to stationary charges, but it has this component, a time-varying magnetic field or a time-varying magnetic flux, which is how we're going to calculate it on a bounded surface, the surface inside the path, determines so we can also write this as EMF equals the rate of change of magnetic flux. And the sign, again, the sign is just the direction issue, the right-hand rule. And then we have the Ampere Maxwell Law, which says that the integral of, we just wrote that down. So the integral of B dot dl is mu 0 times the current enclosed plus mu 0 epsilon 0 d dt. I'll just write the electric flux. Okay. So we have these four equations that are Maxwell's equations. And they tell us that charges can make fields. So here's the piece that says charges can make fields. Gauss's law says charges can make fields. And the Ampere Maxwell law says moving charges can make magnetic fields. But they also tell us that fields can be made by time-varying fields. So here's a dB dt that can make an electric field. And here's a, I will actually write this out the other way just so we can see inside it. So E dot n hat dA. So we've got this dE dt that can make a magnetic field. And that's what we really want to get out of these equations, the idea that a time-varying magnetic field is responsible for a curly electric field, and a time-varying electric field is responsible for a curly magnetic field. So we have dB dt can make a curly electric field or an electric field. And a dE dt can make a magnetic field. Okay. So think about that for a minute, though. You have to ask yourself, what if we had a time-varying magnetic field that made an electric field, but this was varying in such a way that this was actually a changing electric field? Well, then we'd have a time-varying electric field, and that would make a magnetic field. But if this magnetic field is also changing, then we really have fields making each other. So that's interesting. And how would you get this started? We'll see that next time. But what we need is, we need to find an arrangement of E and B that doesn't violate Maxwell's equations. And so we're going to propose one today that's going to work, okay? Not every configuration works, but we're going to propose a possible configuration of fields and show that it satisfies Maxwell's equations and that these fields can just keep each other going forever. And it turns out the key is that the region where these fields are non-zero has to move through space. So this whole thing has to have some kind of velocity. And so we're going to use Maxwell's equations to show that this is actually legitimate. So let's see what this might look like here. So here's just a little animation of a configuration of electric and magnetic field. And as usual, the electric field is orange, magnetic field is cyan. And what we see is you're standing here watching this, and this sort of pulse comes by. I'm stopping it for a minute, but it can't stop. That has electric field in the plus y direction and magnetic field in the plus z direction. And there's this region of space where the fields are non-zero. And then to the right and to the left, the fields are zero. So what happens is this region travels through space. So if you stand here, you don't see anything, anything, anything. Oops, I detect an electric field and a magnetic field. Oops, now I don't detect anything. So our best detector is probably going to be our proton on a spring, and now it's stretching upwards, and now suddenly it's not doing anything. So at our location, these fields are actually varying in time as they go by. Or at any observation location, there's a time variation of fields. So if we stand over here by the left side of the screen, we see the field come by. Now we see it, now we don't. So it's changing in time. Okay? And we've cleverly picked a situation with the electric and magnetic fields perpendicular to each other in such a way that this is going to work. And that's a key thing to remember. There are configurations where it wouldn't work. But this is actually, this is what we're going to be talking about here, but we're going to have to draw pictures of it, and drawing pictures in 2D media is challenging, so it's best to have seen it in 3D. Okay, so what we've got, no nearby charges. We just kind of have this rectangular region of space here, in which there is everywhere throughout the region, not just at the location shown, there's an electric field pointing in the plus y direction, and there's a magnetic field pointing in the plus z direction. And this whole thing is moving that way at some speed v. And there are no nearby charges. So again, if you stood at some location and you just detected electric field with your proton on a spring, what you'd see is a function of time, nothing, 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 and then when it goes past, you'd see this non-zero electric field, and then now it's gone and you don't see it anymore, okay? And you'd see the same thing for a magnetic field. It'd have a different value, but okay, does that make sense? So what we're going to do is just see if this works with Maxwell's equations. And so this is kind of a long chain of reasoning, but we're gonna do it together. So the first one is Gauss's law, and that's pretty easy. So we have this region of non-zero. We're just going to think about the electric field for a minute, okay? Non-zero electric field moving to the right at speed v. The electric field is uniform everywhere. So we use this box as our Gaussian surface, okay? And we measure the electric field all over the box. It's uniform everywhere. And so the question is, what does Gauss's law tell us about what's inside the box? This is not as good as it should be. So you might want to review Gauss's law. We do have a test next week on chapters 21 and 22 and this piece of 23. So you need to know this. So the answer is nothing, zero net charge, and let's see why. So the flux on the top of the box is going to be E times the cosine of 0 degrees times the area of the top. And so that's just E times the area of the top. The flux on the side, well, any side, you see that the angle between E and n hat is going to be 90 degrees. So we have E cosine of 90 degrees area of the side, which is just 0. And that's true for all sides. The flux on the bottom, we have E cosine of 180 degrees area, which is the same as the area of the top here. So this is 180 degrees. So that's a minus E times the area of the top. And so the net flux is going to be 0, and the charge inside equals 0. Okay. And we could do the same thing for Gauss's law for magnetism. We would have our magnetic field is, we basically rotate this whole thing by 90 degrees to do that. So we find exactly the same thing, that the flux on the front is positive, the flux on the back is negative, and the net flux is 0. So we have no magnetic monopoles inside. So that's fine. We're happy with both Gauss's law and Gauss's law for magnetism. We do, however, have these time-varying fields, so I'm gonna see what we can get out of Faraday's law and the Ampere Maxwell law. So let's take this view of the situation. What we're going to do is draw a path. So here's our region with E up and B out. And we're going to draw a path that is a rectangle. So this is going to be our path. And we're going to draw it in such a way that the path, part of the path is where this pulse hasn't gotten to yet. So over here, E is 0 and B is 0. And on the left-hand side, E and B are non-zero. Okay, and we're going to take a snapshot at one instant. And let's see, we're going to call the height H. We can call the width W. If we want to. And there's probably out here, so there's still, so we've got it partly in this region where the fields are non-zero and partly not. Okay, and so we're just going to evaluate the flux. We're going to use Faraday's law to tell us something about electric field in here. And we're going to do it at two different times, time 1 and then time 2 is going to be a little bit later. So this whole pulse will have moved over a little bit. So oops. This is time 2. Pulse has moved. Okay. So, and then we're going to take the difference in those to get the difference in the magnetic flux, and then we'll see what we can see what we find out, all right? So that's the game we're playing. So now let's see if we can do this together. So here's time 1. And here's our question. So here's our path. The dotted line is our path. So this is the path. And the shaded area shows the region where the magnetic field is non-zero at this instant. Okay? So what is the magnetic flux through the surface inside our path at this particular moment? We've cleverly arranged things so that the magnetic field is perpendicular to the path. So what's magnetic flux? Remember that magnetic flux is the sum of its B dot n hat times the area, right? But remember, that's the area where the magnetic field is non-zero. All right. So you say 4 is correct. In fact, that is the magnetic flux, because we have to sum up B dot n hat delta A. So it's only the part of this whole area where the magnetic field is non-zero that gives us a contribution. The rest of it, where B is 0, gives us a 0 contribution, right? So in fact, the answer is indeed B times this distance x times h. Okay, now at a slightly later time, so here's our time t2, and what's happened here is that this pulse has moved over to the right a short distance, so delta x is the distance it's moved, and of course that distance is delta x is just equal to the speed times our time delta t, the time between our two measurements here, right? So what we want here is not the total. Well, we're skipping a step kind of. So instead of just getting the flux here and subtracting, what we're going to do is kind of do the subtraction. What we want to know is the change in flux here. Okay, so that the change in flux has to do with is the difference between the flux now and the flux before it moved. And what happened is that there's this little additional region here with non-zero flux now. No. Okay, Claire, so that's a good question. So Gauss's law for magnetism doesn't say there's no magnetic flux doesn't exist. What it says is that if you add up the magnetic flux over a closed surface, it has to add up to 0. And it's just like, so in if we had done here, so here's our Gauss's law for magnetism thing. Notice that there is magnetic flux on the front surface. There's non-zero magnetic flux on this front surface here. It's just that it's positive on the front and negative on the back. And so there's non-zero magnetic flux on both of those surfaces, but it adds up to 0. It's exactly the same argument as Gauss's law in a situation where there's 0 charge here. So we got positive electric flux on the top, but then we got negative electric flux on the bottom. And so that adds up to 0 if there's 0 charges inside. So this is one of these situations where you have to discriminate between no flux and 0 flux, or no something and 0 something. Yeah, so that's a good question. So here, let's get back. So we okay getting back to this now? So we find so here's our path, and our path hasn't changed. And we find that at any time when the pulse is passing over that region, we have a non-zero flux. And so the question is, how much did the flux change between our first measurement and now? So, well, we aren't, no, you didn't get us off track. That's actually really an important question, so thank you for asking it. So what we're actually interested in here, we've had a little practice calculating flux. What we're interested in here is how much the flux increased. So what we want is the flux in this new region that our pulses moved over. Okay, so we want the additional flux in this little shaded piece, this little gray shaded piece of the, is it clear what we're asking? Okay, so there's a discrimination to make in this question here. This is, notice that we're asking for the delta phi magnetic, not the new flux, but the change in flux since the last time. So, so very good, mostly correct. 3 is the right answer. If you said 5, what you calculated was the flux over the whole region. So you calculated the flux at this time, but not the difference between the two. So what we asked for here is the difference between the flux now and the flux a time delta t ago. And so that's the flux in this shaded region, which has a width v delta t and a height h and a okay. So now what we can do is Faraday's law, which says the change in magnetic flux with respect to time is going to be our b v cosine 0 degrees delta t h divided by delta t. And so that actually gives us a b v h. So that's the right-hand side of the equation. The left-hand side, we need the integral of E dot dl around this path. And so let's remember our path. Our path goes, we'll take it counterclockwise. So we're going up along the right-hand side and across the top and down, I'm sorry, up the left-hand side, across the top, down the right-hand side, and back there. And so here's our path. Here, now we're worried about E. And so we find that in this region, E looks like this. And then over here is 0. So what we're going to get, and so our dl, of course, goes this way. So we get on the left-hand side is E and dl are in the same direction, so it's just going to be E times h. So that's the left. Along the top, dl is to the right, but E is up. So that we have a 90-degree angle there, so it's 0. On the right-hand side here, E equals 0. And along here, this piece of it, E is 0 anyway. Coming back along the bottom, 0 here. E is not 0, but we have a 90-degree angle again, so E dot dl is just equal to E times H. So if we put this all together, we have the integral of E dot dl is the change in magnetic flux. And so we have E times H is BV times H. And obviously we can cancel out the H's. So we find that for this to work okay with, so works okay with Faraday's law if and only if the magnitude of the electric field is equal to the magnitude of the magnetic field times the speed the pulse is traveling at. Okay, so we have one more equation to use here, and that's going to be the Ampere Maxwell equation. So we did Gauss, we did Faraday, and now we need to do the Ampere Maxwell equation. And what we want to do here is, so here's our region of non-zero field. Moving that way. And we have E in the plus Y direction, and we have B in the plus Z direction throughout this region. And what we want to do is we want to take a path that's actually going to be in the XZ plane. Okay, so our path that we want to take is actually going to look like that. So we're going to worry about that path, and we're going to worry about the surface. And it's just going to be a whole lot easier to talk about this if we change our viewpoint so that we are looking down from the plus Y axis. So we are on plus Y axis looking down. And so we can redraw this now as what it's going to look like here. Here's our path. And we're going to have E sticking up out at us. So we're going to have E out of the page, and B is going to be down. Okay, so imagine that you're on the plus Y axis looking down at this path, and this is what you're going to see. So we have here our axes, X, Z, and plus Y. Okay, and in this region, n hat is of course in the plus Y direction. So we're going to consider the same. So the Ampere Maxwell law says that the integral of B dot dl was mu 0 I plus mu 0 epsilon 0, the rate of change of electric flux. Well, okay, maybe it is hard to picture. So let's go back to, just for a second, to VPython. Okay, so here we are. Here's our pulse. And we had, so that we have electric field in the plus y direction and magnetic field in the plus z direction. All we're doing here is rotating the camera so that now we're looking down the y-axis and we see the electric field coming out at us and we see the magnetic field going down. And then what we're going to do is just draw a path. Draw a path that kind of looks like that. So what we've got is, so the electric field is in the plus y direction. So we move the camera, so we're looking down, okay? And so B is in the plus z, as opposed to this. So so here our viewpoint is, we are on the plus z axis, right? Looking in. Here our viewpoint is the plus y axis. We've just moved the camera. So what we're going to do is draw our path. So if I were trying to draw it up here, our path would look something like that. Drawing it down here, which just makes it easier to think about, I think our path looks like that. And so now what we do is we're gonna go through basically the same argument. It's going to look almost identical to what we did before with Faraday's law. So the idea is that what we want to do is, here's our path. I'll draw it schematically. At a time t, we have the field, the pulsive fields have gotten to here. And at a time t plus delta t, the pulses traveled a little farther, and we've got electric fields and magnetic field in this region as well. And so the flux on this piece of the region is how much is delta phi, okay? And of course, this distance is a distance v delta t, how fast the pulse was moving, times h, and the v delta t. So we get the change in the electric flux is going to be just the electric flux in this new shaded region. So it's going to be E cosine of 0 degrees times the area, which is just V delta T times H, the shaded area. And so the rate of change of the electric flux is approximately equal to delta phi over delta T, which is going to be EV delta T H divided by delta T, which gives us an EVH. So that's the right-hand side. The sort of dE dt piece. And of course, there's no current there, so. And then the left-hand side, we need the integral of B dot dl around our path. And so what does our path do? Well, it goes up here and across here. And That way and that way. We're supposed to take it counterclockwise, aren't we? Okay, so let's go counterclockwise. So along the top and the bottom, we have B is perpendicular to DL, so that's a 0. And over here, B equals 0. So the only piece that's non-zero is this left-hand side. So we get B times H times a cosine of 0 degrees plus 0 plus 0 plus 0. So that's BH. And so this isn't quite the Faraday Ampere Maxwell law, because the Ampere Maxwell law says that the integral of B dot dl is going to be equal to mu 0 I, which is 0, plus mu 0 epsilon 0, rate of change of the electric flux. So that's 0. So what we end up with for Ampere's law here is the Ampere Maxwell law is we have BH equals mu 0 epsilon 0 times the change in electric flux, which was in EVH, or dropping out the H's. B is mu 0 epsilon 0 EV. So that's Ampere Maxwell. And again, Ampere Maxwell's law says, well, our traveling pulse is fine as long as that's true. Well, where does that leave us? We have these two equations. We've got, so we have E equals BV and B equals mu 0 epsilon 0 EV. So what we're going to do is solve for V, apparently. There's a constraint on the speed at which this thing can be traveling, apparently, to work. So if we just do a substitution, we take this BV and substitute for E, we're going to get B is mu 0 epsilon 0 BV times V, or mu 0 epsilon 0 BV squared. And we can just divide by B here. So we get 1 is mu 0 epsilon 0 V squared. So it looks like V is going to be the square root of 1 over mu 0 epsilon 0 in order for this to work out. Okay, so so V is equal to the square root of 1 over mu 0 epsilon 0. If we just multiply this by 4 pi over 4 pi, we're going to get it's the square root of 4 pi over mu 0 times 1 over 4 pi epsilon 0. And that's going to be equal to the square root of 1 over 10 to the 1 times 10 to the minus 7. So that's 1 over mu 0 over 4 pi times 9 times 10 to the 9th. And so it looks like that's the square root of 9 times 10 to the 16th, which is, of course, 3 times 10 to the 8th meters per second. So this works if V is the speed of light. So this is an electromagnetic wave. It's a simple kind. It's not a sinusoidal wave, but it's this pulse of and it travels at the speed of light. Now, we know some things that have to be true about it. We know that E has to be equal to, we found that E was equal to B times V, but now we know that V is C, so E has to be equal to the speed of light times B. So in this wave, the magnitude of the electric field is equal to the magnitude of the magnetic field times the speed of light. And the direction of motion, so we had E up and B out of the page. And the direction of motion, or direction of what we call propagation, looks like that's the direction of E cross B. So we can write this mathematically as we say V hat, the direction of V, is equal to E hat cross B hat. But don't overgeneralize. So it's don't overgeneralize. So V is not equal to E cross B, no. So don't think this, but the direction of motion has to be given by that. Yeah, who knew that that was going to drop out of just applying Maxwell's equations? I mean, but Maxwell said, this has to be a description of light. There's a very, very short homework assignment on this. It's 4 questions, and they're just easy qualitative questions about electromagnetic radiation, in addition to the homework assignment on Faraday's law. And we will pick this up next time when we can talk about, okay, so we can have electric fields generating magnetic fields, generating electric fields, generating magnetic fields, and as long as this thing is propagating through space, it works, but how do we get it started? And that's going to be our topic for next time. We don't need any charges. It can be going through a vacuum, apparently, quite happily with no charges around, but how do you get it started? And that does involve charges, and so that's our topic for next time. Okay, so in recitation today, we will mostly be practicing a little more with Faraday's law. Although we can talk about this if you want to. Okay, so what did you learn today?
Dr. Chabay?
Yeah.
So is this basically saying, I feel like this is something I already know, but I never thought about it like this. Is this basically saying that that light is basically just a pulse of an electric field going one way and a magnetic field going another way?
Yep, that's what it's saying.
I mean, I feel like I've heard that before and I've understood it. I just never thought, I don't know, something about hearing it this way makes it seem more different and odd.
Well, it is odd because the question, I mean, the question that you probably never thought to ask, but how could that work? Don't you need charges to make the fields, right?
Yeah, I guess because I also always thought of light as not necessarily matter, but as kind of, I don't know, it's something is there as opposed to it's just 2 fields.
Oh, I mean, it sort of makes you think about the reality of fields, doesn't it? Like, I mean, light seems to be real. If light is just made of fields, then these fields must be pretty real.
Yeah, this is I'm gonna get lost thinking about. Okay, thank you very much.
There's a lot to it.